So we looked at the role of alloying elements, how these alloying elements behave during solidification of the weld pool. Okay, so now we'll move on to the other aspect in the development of microstructure. In the heat affected zone, how the microstructure can change during applying Weld thermal cycle, while applying Weld thermal cycle. So we looked at the microstructure of trip steel, for example, contain 3 important phases: ferrite, the carbide free bainite, and retained austenite. And so when the temperature is reached above the A3 temperature, the austenite formation temperature, the entire microstructure what is shown over here would completely transform into austenite. But then you would also have regions in the heat affected zone where the peak temperature reached is less than the austenite formation temperatures. So then you would expect the austenite would also change its morphology, or it may also even destroy completely during heating. So we will have to understand how the retained austenite fraction change in the heat affected zone and based on the peak temperature reached. So we already looked at the variation in the peak temperatures when you move along from the weld center line. So suppose if this is your weld center line, and when you move or going away from the weld center line towards the base material, your peak temperature would range from close to melting, and then it will go to room temperature and far away from the weld. And so the regions where the temperature reach to temperature below the A3 temperature, the austenite formation temperature, then you may expect this retained austenite would completely destroy. But we need to understand how the microstructure can change when you heat up the material in the heat affected zone to temperatures ranging from say room temperature to A3 temperature. So regions where you would expect no transformation, but you may expect the change in the microstructure. So we will see what happens to retained austenite in the microstructure, because retained austenite is a very important constituent to get the properties of the trip steel, or even in complex phase steels, and we may have to have one retained austenite to achieve the combination of strength and ductility. And first of all, we need to look at what are the techniques available to quantify retained austenite in steel microstructure. So once you have these techniques ready, then we can analyze the retained austenite concentration in the welds, and then based on the measurements carried out at varying regions in the mill, and we can see how the austenite concentration change as a function of the weld thermal cycle. Because weld thermal cycle is not as a typical heat treatment done to a trip steel, right? So you may have the peak temperature varying from say close to melting point, even above melting point fission zone, to room temperature when far away from the weld center line. So some of the common techniques we use to quantify retained austenite in steels, we can use a simple optical microscopy with color etchants. Like for example, this microstructure was made using a color etchant, and where we can see the presence of 3 phases very clearly, and you have an alpha. So you have the alpha matrix, and you have the brown color here is a carbide free bainite. Carbide free bainitic ferrite, and the bright islands over here you see these are all retained austenite, as I explained. So now we can use a simple point counting method to calculate the volume fraction of individual phases, but again it may not be accurate compared to the other techniques which is listed over here, because what you are seeing over here, it is not a representative full representation of the volume. So some of the techniques like the magnetic saturation method, which can be used to measure the retained austenite concentration in bulk in the entire sample. I will explain the principles in subsequent slides. And we can also use an extra diffraction. An extra diffraction gives the quantitative information from the diffraction peak analysis, and we will also see in subsequent lectures how the X-ray diffraction can be used to quantify the retained austenite, and some other uncommon methods, and they are sophisticated techniques to quantify retained austenite. For example, you can use the electron backscattered diffraction (EBSD), or thermal diffusivity, laser ultrasonics, or thermoelectric power measurements. In this case, the magnetic saturation, and to some extent even use in a synchrotron X-ray diffraction. You may also measure retained austenite in bulk or in the entire volume. EBSD is again similar to an optical microscopy, where we have only two-dimensional imaging, so that you may get only the retained austenite fractions at given locations of the scans. And the thermal diffusivity method work by measuring the heat transfer as a function of microstructural constituents, and then by changing the transfer characteristics, we can also measure the exact amount of retained austenite. And we can also use the laser and ultrasounds, where from the attenuation velocities of the laser and ultrasounds, we can clearly see the difference in the microstructural constituents, and we can quantify from the attenuation the volume fraction of retained austenite present in the microstructure. And same goes with the thermoelectric power measurements. We use the Seebeck effect to understand the variation in the microstructures, and by seeing the variation in the EMF generated as a function of microstructural constituents, we can also measure the retained austenite concentration. But the most common method is used for quantifying retained austenite in steel is the magnetic saturation method. So why magnetic saturation method? Because when you look at the microstructural constituents of steel, the austenite is paramagnetic. That means it is non-magnetic, and compared to the other the commonly present microstructural constituents. For example, ferrite is ferromagnetic, and cementite is ferromagnetic below Curie temperature, and martensite also ferromagnetic below Curie temperature. So by measuring the paramagnetic microstructural constituents quantity, so we can also measure the quantitatively how much amount of retained austenite present in the microstructure. So the technique we use for measuring retained austenite is known as vibrating sample magnetometry. So you can refer in literatures how the technique work, but I will explain the principle how we measure the retained austenite concentration using this technique. So how we get the retained austenite concentration is to get the saturation magnetization values. So we measure the magnetic the saturation or mass magnetization as a function of applied magnetic field strength in Tesla. So we have a typical magnetic hysteresis curve we must have studied in +2 physics. So we generate such a magnetic hysteresis curve, and if you look at this curve, and typically when you start applying a magnetic field, the ferromagnetic material get magnetized as a function of the applied field, and then upon reaching a critical field strength, the magnetization saturates to a value, and this saturation value is known as magnetic saturation, MS, or saturation magnetization. And this MS value, the saturation magnetization value, change if you introduce paramagnetic constituents in the microstructure. For example, if you have a fully 100% ferromagnetic material and you have an MS value, say for example this value corresponds to 100% ferromagnetic microstructure. So now you introduce on retained austenite into this microstructure. That means that you are introducing some component of paramagnetic constituent. So then the magnetic saturation decreases. It may not be in this value, so you may expect a saturation value decreases compared to a microstructure with completely ferromagnetic constituents. So the difference between the structure with 100% ferromagnetic to the saturation values with the paramagnetic constituents, this difference can give us quantitatively how much amount of paramagnetic component is there in the microstructure. So that means that by measuring microstructure saturation magnetisation value with and without paramagnetic component, and we can see we can quantify the retained austenite concentration which is paramagnetic in the microstructure. So a typical mass magnetization curve for a trip steel I have given. For example, in this case the top curve is without retained austenite for a typical trip steel the composition. These measurements were made for the high silicon steel, which showed in the previous lectures. And if you look at it by changing the intercritical annealing temperatures and intercritical annealing temperature and isothermal binetic holding temperatures, and we may also change the retained austenite fraction in the microstructure. So in one case, in the first case, we have a microstructure without retained austenite, and we have 100% ferromagnetic material. And by introducing the paramagnetic component, your magnetic saturation value decrease compared to the microstructure without retained austenite. So by calculating the differences, we can calculate how much amount of retained austenite is there in the microstructure. Okay, so that is the basic principle behind using the magnetic saturation method, where we measure the magnetic saturation value with and without retained austenite, and the difference would give us the amount of retained austenite present in the microstructure. Right. So the equation goes like this. So the volume fraction of retained austenite F5 which is nothing but 1 minus a coefficient which takes care of the presence of non-metallic inclusions. So generally these non-metallic inclusions can also be paramagnetic. So the beta takes care of the presence of other non-metallic phases which are paramagnetic, and generally if you don't have inclusions in the microstructure, and this goes away, and then the ratio between the magnetic saturation without austenite to magnetic saturation with austenite would give you the fraction of retained austenite present in the microstructure. So MSF is the MS, the saturation magnetization without RA to the MS with RA. So this would lead to the calculation of RA volume fraction in the microstructure. So this is the basic for the measurement of retained austenite using magnetic method, where we measure the saturation magnetization and with and without retained austenite, and then we can calculate accurately from the saturation values the amount of retained austenite present in the microstructure. And the same technique can also be used to understand the stability of retained austenite in the microstructure, especially for example in the heat affected zone, and we may also heat up the microstructure to various temperatures and then cool down, and we will also have to understand how the retained austenite stability is affected by this heating. So you can clearly see here, what you see over here is the MS, the magnetization measured as a function of temperature. So if you look at this at room temperature, that is the room temperature mass magnetization value in a trip steel, at room temperature. So when you have a trip steel containing microstructure heated up, retained austenite containing microstructure heated up to higher temperature, so what will happen then? Your retained austenite, what you see over here is the magnetization decreases as a function of temperature effect, and once you reach a critical temperature, your retained austenite present in the microstructure is transforming into the another phase, which is ferromagnetic. So what implies this reaction is you have a retained austenite containing trip steel, but when you heat it up, your MS, the mass magnetization saturation suddenly increases upon reaching a critical temperature, for example in this case around 300 degrees centigrade. That means that the microstructure is becoming more ferromagnetic, right? So if there is increase in saturation, what does it imply? It implies that your the microstructure is now becoming more ferromagnetic. That means that something happens to retained austenite, and retained austenite is converting into more ferromagnetic structure, and we will see in subsequent slides what happens to retained austenite. Now we can see from the measurements of magnetic saturation over a temperature, and you would see an increasing saturation upon reaching critical temperature, and that can happen only when the microstructure becoming more ferromagnetic. And you also see that some other the change in slopes. So during this transformation we also see sudden decrease and increase in saturation values during heating, and subsequently when you increase the temperature further, and you would expect a thermal effect leading to a decreasing saturation. So this sudden change in slope we can relate to the decomposition of retained austenite during heating. So what happens when you heat up the retained austenite containing microstructure is the retained austenite present in steels is transforming into the mixture of ferrite and iron carbides in the steps described in this equation. So first retained austenite is transforming into ferrite and an epsilon carbide. So epsilon carbide is another transient carbide you would expect when either austenite or martensite is tempered. So what you will see over here is when retained austenite is heated up to higher temperature, retained austenite is transforming into ferrite and transient carbide mixtures, and ultimately leading to a formation of equilibrium structure, which is ferrite and cementite. So what happens here when you heat up the retained austenite is retained austenite is decomposing into ferrite and epsilon carbide mixture, and then subsequently you may expect an ferrite and eta carbide, and then ultimately ferrite and eta carbide mixture will change into ferrite and cementite mixture. And how do we know that there is a transient carbide formation? And if you look at the magnetic curves, you also see a decreasing in magnetic saturation values when you are doing it. These transient carbides are also paramagnetic carbides. So therefore you can understand very clearly that when retained austenite transforming into the ferrite and cementite mixture, and you expect an increasing ferromagnetism because of ferromagnetic ferrite forming from retained austenite, and subsequently because of the transient carbide formation you will see a decreasing in saturation, and once you have complete transformation of retained austenite into a ferrite and cementite mixture, then you will have a ferromagnetic microstructure. So what this implies is, if you look at the onset of transformation of austenite during heating, so you expect a transformation of austenite to ferrite. The temperatures are around 300 degrees centigrade. So that means that in an actual in the welding case, so when the peak temperature in the heat affected zone reaches even as low as 300 degrees centigrade, you expect a change in microstructure. So therefore the heat affected zone the width of the heat effect zone compared to conventional steels, where you won't see any change in the microstructure when the temperature reached to 300 degrees centigrade. Whereas in trip steel, so we expect a significant change in the microstructure because of the transformation of retained austenite. So we'll summarize here. So we looked at the variation of retained austenite along the microstructures of the heat effector zone, and we also looked at the stability of retained austenite as a function of temperature, and what are the techniques we can use to measure the retained austenite in the weld microstructure, and we move on subsequently in next lectures how the retained austenite fraction vary as a function of peak temperature reached in the heat effector zone.